We're now going to take a look at other Kubernetes DR considerations. Now, we just want to quickly go over, there are different styles of managing the Kubernetes cluster. One is the imperative way of administering the Kubernetes cluster, in which we use commands like kubectl create, edit, or delete to manage the cluster, to create Kubernetes resources. This is typical way of managing systems in the past. This is what what would come naturally. The other approach is to use configuration files, which are also common in some systems, where you provide an input file to again create, replace, or delete. In Kubernetes also offers this method, but there are some limitations of this imperative method using even configuration files. Now, if you use either of these two methods, you should note that the changes that you're making are only preserved according to your backup schedule. So again, similar to the data loss we spoke about, a similar configuration loss can occur if you made change between the replication window where you might not have the cluster changes appearing on the other side. The other alternative is using a declarative source. This is a little bit complex, but it offers some certain advantages. So this is the method of using kubectl apply -f and a directory, right, to manage the cluster. It contains a bunch of YAML or JSON files. You could also use kubectl diff to preview the changes before applying. And note that wherever the source of these files are kept, we don't want it to be in a laptop, right? We want it to be protected in a better place, preferably in Git. So we're going to talk about that a little later. Now, what are the other DR considerations? Now, note that we are replicating, we are taking a backup, but if there is a corruption to the PV data content at the primary, the replication or backup will faithfully replicate it or take a backup of it. Hence, you need to use PV snapshots to protect the PV. The other point is, the second point is about the definition of what an application is in Kubernetes. Now, this is not a Kubernetes problem per se. This is also there in the traditional world, where how do I find out all the related pieces of an application? The point here is Kubernetes, while it solves a lot of problems, but it still doesn't solve completely as to, is there a command that I can run and find out all the dependencies, all the dependent CRDs, all the dependent operators, etc. Still not there, right? So you need to figure out, how do I have all this on the other side, on the failover cluster? And then how do I handle networking, cross-cluster networking between these DR peers, right? So that doesn't come out of the box in Kubernetes. That requires an add-on. The other thing is the image repository, right, where your images are coming from. So they need to be available across these DR peers so that when you're failing over, these images are available. The last point is the PVC to PV binding in the case of dynamic provisioning, right, on failover and failback has some nuances that are dependent on the DR solution. Now Shyam is going to talk about our approach to DR that addresses these issues. Shyam?
Thanks, Veera. So let's start with the biggest gap that we had, which was in the cross-cluster services, right? So if you look at the next slide, what we propose is a multi-cluster control plane, which is essentially another Kubernetes cluster, but it in turn manages the DR peers, or not DR peers for that matter, the other Kubernetes clusters that are the DR peers. This particular multi-cluster control plane hence has enough access to do various things with these Kubernetes clusters. So let's map the first couple of services that we were talking about. The DR orchestrator, which is the cross-cluster service that we talked about, can very easily fit into the multi-cluster control plane. It can shift applications across these clusters, fail over, fail back, ensure data mobility, availability, and so on. And so that's a service that can be lifted up to the multi-cluster control plane. We always looked at the global traffic manager as a service which lies outside the Kubernetes clusters because it does, and needed to be managed separately or outside of the Kubernetes clusters in that sense. So again, the multi-cluster control plane provides a nice layer for us to have a GTM orchestrator, which can actually orchestrate where the global route should be routed to, rerouted to. Maybe the DR orchestrator itself can, manage the GTM custom resources to reroute application routes, so on and so forth, increasing our automation steps. The multi-cluster control plane can also be enhanced with the health monitor, which we spoke of earlier. That can come as a service. Again, the DR orchestrator can feed off the health monitor to know when a cluster is down or up, and hence move workloads around or alert users or administrators that a disaster or an unavailability of a cluster has occurred and somebody needs to take action. The last one, the configuration policy manager, is again an interesting service that can be built. This can help keep the configuration of the DR cluster peer clusters equivalent to each other, right? So we've been talking about custom resources, custom resource extensions that an application may depend on. How do you ensure these custom extensions are available in all the peer clusters so that you can not worry about those application resources and just worry about the core application resources and deploy them on the various clusters? So some form of a configuration policy manager is useful to make that happen. So just a word of just an observation here. We're basically relying on the upstream project Open Cluster Management, which is a multi-cluster manager layer built to do some of these functions. And we're thinking of extending and expanding that with the DR orchestrator and possibly the GTM orchestrator and so on. Now, in terms of application deployment and application resources, Veera just covered imperative and declarative management of these resources. So in our approach, we're kind of going down the declarative source. This is actually how Open Cluster Management also does it. And what this provides us is you don't need to back up these application resources. Your RPO on these application resources is 0, just like Veera mentioned. And not only that, if you have multiple application sources which need to actually be grouped together, the application deployment controller, which will kind of have two functions, can group various declarative application sources and drop them into the peer clusters as a group. Not only that, it will also help keep in sync what's running on the cluster with any changes to the Git source or the repository where these declarative resources are present. So we kind of completely handle. We don't need to back up application resources anymore, and we can just completely handle all this. Now, this leaves storage, right? So in the next slide, we start talking about storage. But what our core intent in storage is basically to enable management of replication from Kubernetes layers, but actually leverage the storage assisted or storage provided replication mechanisms of various storage vendors that's already in place, right? So the management layers comes from Kubernetes, whereas the storage replication is done by the storage vendors. What this means is the storage vendors are setting up replication across vendor, storage clusters is outside the scope of the DR solution as such. It can be another configuration setup, which can come from the multi-cluster control plane. For example, Rook does that with Ceph. But basically, that's not dealt with. But storage is set up such that storage replicates to the DR peers, and the Kubernetes clusters are using those DR peers locally for the PVPVC store. Before we talk about how we enable Kubernetes to manage storage-based replication, we need to take a look at CSI, which is basically the container storage interface. Click next, Veera. So the container storage interface is being defined as an industry standard. I'm just going to read this out. That will enable storage vendors to develop a plugin once and work across a number of container orchestration systems. Kubernetes is one such container orchestration system, supports CSI, and typically the CSI storage plugins are responsible for volume lifecycle operations like creation, deletion, resize, snapshot, clone, various things that we've already talked about. So when a PVC comes in, the storage plugin is the one that actually creates a volume, and the PV is updated with an endpoint to that volume for use by the application. So what we propose is to extend CSI to support the management of a storage plugin assisted replication by a new custom resource called volume replication. The volume replication custom resource will act at a granularity of a PVC. In other words, it will point to a persistent volume claim that needs replication. It'll have various lifecycle operations like enable, disable, mark something primary, mark the peer cluster secondary, where primary means it's the source of data synchronization and secondary means it's the target of data synchronization. Typically, it'll be primary on the cluster where the app is running and secondary everywhere else. When the cluster goes down, another cluster will be forced primary, simply because it cannot be made primary in agreement with the old primary. Cluster is no longer available. And so that's where the data loss will occur, depending on the storage vendor provided replication mechanism. So if it's synchronous, 0, if it's async, snapshot based, whatever the storage layers do, the data loss will be equivalent to that. So volume replication extension is what we provide. Now, what does this mean for the user, right? So the user, in addition to deploying application resources like PVCs, also need to deploy a volume replication CR, which will point to the PVC and which will have a particular state of primary or secondary. Now, the user can do this, or the DR orchestration layer can do this. That's immaterial, but at a very low level, the user could also manage the volume replication state using this particular custom resource. And of course, any storage vendor can have their storage, their CSI pods or their CSI storage plugins expanded to support the new CSI verbs, and hence provide for storage replication. So however the CR changes, the storage plugin reacts to that and makes it primary or secondary. This is not yet upstream. We're just looking at it right now. We're developing some code and spec around it, trying to see if it works for some of our use cases. And we intend to take it to the data protection working group, but just letting people know that it can be perceived as a custom extension as it stands, but it's available to all. We'll look at that in the links later on. So this is how we intend to handle storage assisted replication and moving, managing that via Kubernetes. So now let's take a checkpoint. Let's revisit the DR requirements that we laid out. We might be missing something. So, well, of course, we don't get check marks for that. But basically, we've covered application resources using declarative sources primarily. We've taken care of dependent custom resources using some form of configuration policy management. We've looked at application data, enabled kube-based management for that. Cross-cluster services, we're looking at an entirely new cross-cluster service plane, which actually serves as a single pane of glass for us to provide health monitoring, the external traffic routing, DR orchestration services in that common cluster plane. Of course, it can be extended to do other things. So this approach seems to get us nearer to the more automated DR workflows. Still be a single click left for the user or the administrator to accept the data loss, as Veera has talked about. But the rest of the steps can be automated and coordinated across clusters using such a scheme. So with this, let's also go ahead and take a look at what is the evolving Kubernetes landscape. Let's look at what else is coming up there. So typically, we talked about dependent applications, but usually applications need not have single volumes that need to be protected. They have a bunch of volumes which need to move in lockstep, right? They need consistent snapshots. All volumes should be snapshotted at the same time. The replication that we're talking about should happen for all volumes to the same consistent point in time rather than a volume racing ahead of the other, because that's not what the application wants to see. So this brings about the notion of volume groups. It's not something that is new, but volume groups in Kubernetes does not exist as such. The enhancement proposal is out there. It's been a lot of discussion. A lot of storage vendors are participating in it, so that it serves all storage vendors and not some only cloud-based storage or otherwise. So that's going to be very useful. That can be leveraged for replicating groups. The next one is, till now we've been looking at snapshots. We've been talking about snapshots, CSI snapshots. These are all storage consistent snapshots. These are not application consistent snapshots. They just let the storage plugin know that there has to be a snapshot, and storage can only create a storage consistent snapshot in that sense. For getting into application consistent snapshots, there are ways around that where people say run stop the application, take a snapshot, and then start the application back up again. Well, yes, that's one way to do it. But they upstream against working on the data protection working group with the application working group. They're working on things like container notifiers, so that application containers can be notified about a snapshot, can query the data, give a go ahead. Snapshot can be taken to the storage layer via CSI, and then the application containers can be notified again that they can go on and continue writing, performing their IOs or IO operations. That can be followed in the link as provided there. Moving on, let's take a look at three other interesting things that are happening. There is a very early stage proposal on change block tracking. So we've been again talking about snapshots, but if you look at the backup slides that we talk of how to back up, it's mostly a full backup. You take a snapshot and then you slurp all the data and put it into an data vault, right? But there is some building concept of change block tracking across snapshots, so that you only get the snapshot deltas that can be transferred across at a cheaper cost, right? So you can take full snapshots, and then you can do an initial full volume backup, and then later on you can just do the snapshot deltas. That's just in the proposal phase, and that's why there's a doc. If that's of interest, if that helps you build your solution, that's something that you need to go and look at. We also come to another interesting concept called data populators. This is almost beta as of the current release. So Kubernetes goes where 3 gates, alpha, beta, and GA general availability. So once it's GA, the API is supported, and backward compatibility and such is ensured. So that's good. I think data populators right now at beta, very soon to be GA, probably in the next release. Data populators give you this ability. Data populators is something that we already know what we talked about. So when you create a snapshot, how do you recreate a volume from a snapshot? So you create a PVC and you mark a data source as the snapshot. How do you clone from a volume or clone from a snapshot? You mark a PVC, you mark the data source as a volume or the data source as a snapshot. So Kubernetes only understood a data source as a snapshot or as another volume. Data populators is extending that to any arbitrary cluster resource, custom resource, so that volumes can be populated with that as the data source, whatever it means. For example, we could put volume replication as a data source and populate it on the other end, giving us a clone of the point-in-time replica rather than pointing to the replica itself. So there are things that can be done with data populators. Volume backups has become a hot topic. It's under discussion in that document. It's for backup, but it definitely has its use cases. It does talk about incremental differential and so on. It's again early stages, but it's a good time to participate and get more done there. So these are some of the Kubernetes enhancements related to data protection in that space. Our call to action, based on all that we've been talking about, is, hey, if you want to participate in the approach that we laid out for the multi-cluster control plane, disaster recovery via the multi-cluster control plane, volume replication, so on, this is where most of the work is happening. As I said, the Open Cluster Management project is what we're using for the multi-cluster control plane. It's out there. It's got a whole bunch of version 1 APIs, which means it's GA supported. It's not a nascent project in that sense. Whereas the DR orchestrator and the volume replication CSI add-ons that are the next two links are in their infancy. We're just designing the alpha APIs, writing some code to get that going. But those are essential for DR. So if you please do take a look or help us out, as the case may be. From other call to action, if this is a hot topic, this is something that is really interesting and that you need to participate in. These are the working groups, the storage working group and the data protection working group. Sorry for the acronym there. That you can participate in. They have weekly, bi-weekly or monthly meetings and various topics. All the topics that we talked about, the future stuff get discussed there, and it'll be very useful to participate in those working groups. And lastly, we have our presenter information there. You can reach out to us for further questions, comments, discussions, as the case may be. With that, thank you, and please do leave session feedback so that can help us do better next time.
That's right. Thank you, Shyam, and thank you all for joining today. Please do give us your feedback. Thank you.